This lecture will be over sections 6.3 and 6.4. They won't last very long, uh, but we've already discussed photons' interactions with matter and the interaction of charged particles with matter. The one thing we have not talked about is a neutron interaction with matter. Now, a neutron is not charged. In addition to that, it's not really a photon, so how does it interact with matter? Um, you've got two reasons why it's important in radiation therapy. High energy linear accelerator beams do have a neutron contaminant. They don't contribute significantly to patient dose and the treated volume, but they do pose a radiation safety hazard. We'll get to that in further sections, further chapters. In addition to this, for proton therapy facilities, one of the major radiation safety issues is neutrons set in motion by high energy protons. Second reason is that there's a small number of facilities that treat or have treated patients directly with neutrons, either by external beam or brachytherapy. So we've discussed neutron activation in chapter 3. This is of importance for the production of medically useful radioisotopes and is occasionally of relevance in radiation safety. It's not of importance in the treatment of patients with neutron beams. Activation of certain components, like the flattening filter of linear accelerators, can be of significance during maintenance of these machines. The flattening filter of a decommissioned high-energy linear accelerator may have a significant amount of activity. In this case, the flattening filter, you just can't throw it out. Neutrons, like photons, are a form of indirectly ionizing radiation. So they must first transfer their energy to the charged particles, and then the charged particles deposit their energy in the matter. So photons interact predominantly with electrons. Um, photons interactions are therefore dependent on the target material's electron density, and that's independent of the elemental composition of the absorbing material. In other words, the Z value doesn't really matter. Neutrons interact primarily with nuclei, and these interactions are highly dependent on the chemical composition. So this can be quite complex, and in human tissue, you're looking at hydrogen, oxygen, carbon, and nitrogen. So you got two major categories. Neutron can scatter from a nucleus in the target material, changing direction and losing energy in the process, or it can be absorbed by the nucleus and replaced by secondary radiation. It could be that secondary radiation can be a gamma ray, a proton, alpha particle, and the nuclei of the absorbing material itself. These secondary particles can be produced by neutron-induced nuclear reactions. So for energetic neutrons, the predominant energy transfer is elastic scattering with the nuclei of the material itself. When it collides with the nucleus, it transfers some of its kinetic energy to the nucleus, causing it to recoil. Think of like playing pool or something, having a cue ball strike one of the other balls. It's going to cause it to recoil. You can see the most efficient energy transfer with hydrogen because they're about the same mass. The neutron, yeah, that's just exactly what I just said. When a neutron collides with a proton, it can give up all of its energy in a single collision. However, when it strikes a heavy nucleus, it can only transfer a portion of the kinetic energy in any single interaction. And it goes on to discuss the billiard part, billiard analogy. There we go. Get it out in a minute. Once they've slowed down sufficiently, they can be captured by the nuclei. When it's captured, the nucleus can be left in an excited state and emit a gamma ray. The neutron comes in, is absorbed, and a gamma ray goes out. This is important in radiation shielding because when neutrons are absorbed by shielding material nuclei, they emit gammas, which they must be shielded for. The neutrons must be attenuated first, then the gammas released by the absorption of the neutrons must also be attenuated. So that's why those suckers are pretty thick. Efficient absorbers of neutrons are hydrogen-rich materials such as human fat, paraffin, wax, polyethylene, concrete. Although lead is a good material for shielding photons, it's very poor against neutrons. Predominant mode of energy deposition from fast neutrons is due to the recoil protons. So the low energy recoil protons have a much higher linear energy transfer than the electrons. Cherenkov, that is how you say that, Cherenkov radiation. Sometimes patients will report seeing blue flashes of light during treatment, even when their eyes are closed. Here's the note about that. Astronauts have reported the same phenomenon during spaceflight. Most likely, the production of Cherenkov radiation in the individual's eyes. It's visible radiation in the blue portion of the spectrum. It is the cause of the blue glow that you sometimes see in the photos of nuclear reactor pools. It's produced by the passage of charged particles through matter with a speed greater than the speed of light in matter. That's not a violation of the special theory of relativity because light travels more slowly in matter than it does in a vacuum. The theory of relativity prohibits an object from traveling faster than light in a vacuum. And if you want to see a picture of it, this is what they're talking about. So it's Cherenkov radiation in water by 10 MeV electrons. This shows the setup before the beam's turned on. This shows the characteristic blue glow associated with Cherenkov radiation due to electrons incident from the right-hand side. The intensity diminishes towards the left as the energies lose electron water, which is what you're seeing. It's bright over here, not so bright over here. Okay, well, that's the end of chapter 6 lecture.